is ionic or molecular. Okay, so an ionic compound is formed from electrostatic attraction between oppositely charged particles. So that means cations and anions, okay? Electrostatic attraction between cations and anions, right? Because they have opposite charge. So what forms cations? Metals, generally speaking, right? What forms anions? Non-metals, generally speaking. So 9 times out of 10, maybe even more than that, if you've got a metal and a non-metal, you're going to be looking at an ionic compound. Sometimes you will have what's called a polyatomic ion, which means there's 2 or more different elements bonded together, and then they become charged to form a poly. That means many atoms in an ion. And there is one I want to draw your attention to, which is the ammonium ion, ammonium, which is NH subscript 4 superscript plus. Notice nitrogen and hydrogen are both non-metals, but that forms a cation. So it is feasible. Sometimes you'll have a compound with like the ammonium cation in instead of a metal. Sometimes it's called a pseudo alkali metal that can contain all non-metals. So that's like one little exception to watch out for. So what's a molecular compound? So molecular is sharing of electrons. So who is going to share their electrons? It's going to be between non-metals, okay? So no ions are formed, okay? So ionic bonds is electrostatic attraction between ions, okay? So if you like to think of it as a complete transfer of electrons, okay? Because what do cations do? They lose electrons. Where do those electrons go? They grabbed up, I guess, by the anions, right? That's where they go. So they've been transferred from the cation to the anion, and then those 2 particles get mushed together by electrostatic attraction. If something's molecular, then the electrons are shared between the non-metals. So that's going to be always metal and non-metal. Yeah. So molecular compounds, that kind of harks back to what we were talking about in chapter 1, about that you can have variable compositions between the same 2 elements, like carbon monoxide, carbon dioxide. You see that very characteristic of molecular bonding. Anywho, so your quick and dirty way of answering this is to look at the compound and look at whether it is a metal and a non-metal or 2 non-metals together, okay? We will learn more about polyatomic ions soon, okay? So ammonium is an example of a polyatomic cation. We've also got loads of polyatomic anions, one which you've probably met as carbonate, CO subscript 3, superscript 2 minus, the carbonate ion. So you can see within polyatomic ions is usually molecular bonding within the ion, and then that group of atoms bonded together by molecular bonds becomes charged, but then that acts as an anion usually, or a cation, so then takes part in ionic bonds. Okay, so magnesium is over here on the left side of the periodic table, so that is definitely a metal, and phosphorus over here on the right side of non-metal. Remember, we've got this ziggy-zaggy line here which separates off our metals and our non-metals. Okay, I should probably move that this way a little bit, but these are the metalloids in between the gray area. Okay, so magnesium 3, phosphorus 2 is going to be ionic because it's a combination of a metal and a non-metal. Bromine and oxygen, BrO2, or bromine's over here in the halogens, oxygen's over here in the chalcogens. So those are both non-metals. We're going to go molecular with that one. HCl. Oh, this is a good one to mention, okay? Because hydrogen. Why is hydrogen green and all the other guys yellow here? Because hydrogen, no matter that sometimes it sits over here, often you see a big gap here. Hydrogen is a non-metal, so be really careful. Hydrogen is a non-metal, okay? That's the only one over there, okay? So if you see hydrogen bonded to another non-metal, that is going to be molecular, not ionic, okay? It does form a cation though, which is kind of cool, right? But the bonding in HCl is technically molecular. Same for HF, HBr, HI. So watch out for those ones. Okay, let's have a look at another one then. What have we got? HNO3. What a lovely example. Okay, these are all non-metals. Okay, so we're going to go with a molecular compound But do watch out because NO3 minus is the nitrate anion, so that can also form ionic compounds. But in this case, they're all non-metals. We're going to go on the metal, non-metal category for this question, unless we come against ammonia. Okay, barium is a metal. This is the acetate ion, C2H3O2 minus, so it takes two of them to balance out the barium. Let's just get used to the idea of how ionic compounds of are balanced. Okay, so it's ionic. Calcium is a metal. Chlorine's a non-metal. Okay, so that is an ionic compound. So while I've got this screen up, just to help you out for future endeavors, so do notice how these ionic compounds are charge neutral. They have to be, right? So look at barium, it's a group 2 metal, so we know it's barium 2 plus, okay? And this acetate ion is C2H3O2 minus. So it's going to take 2 of this acetate ion to balance the +2 charge from the barium cation. And look, in the formula, there's a brackets and the subscript 2 outside is telling us we have 2 chunks of acetate ion for every 1 chunk of barium cation. Okay, same here with the calcium chloride. Okay, but that's a monoatomic ion that we have calcium 2 plus and chlorine is Cl minus, so it takes 2 chloride anions to balance 1 calcium 2 plus cation. So when you have a polyatomic ion, notice that they are enclosed in parentheses to show it's the whole thing that is the ion. So that is a very useful thing to point out at that point. Okay, so use the periodic table as your guide, and you should be able to identify metal and non-metal, ionic, non-metal and non-metal.